Okay, let's look at this example 9, independence. A card is drawn from a standard deck of 52 cards, and then a second card is drawn without replacing the first card. Let A be the event that the second card is a spade, and let B be the event that the first card is a spade. Determine whether A and B are independent. So we're going to draw a second card without replacing the first card. So intuitively we should expect that the events are not independent, since the chance of getting a spade on the second card are better if a spade is not removed from the deck on the first draw than if one is removed. Let us confirm our suspicions mathematically. To show that A and B are not independent, we can proceed in one of two ways. We can either do it this way, show that this is not equal to that. That would mean they're not independent. Or we can show that this is not equal to that. That's the same thing, remember. Or this one is also the same thing. So we're going to do it this way. So remember that you can show any one of these things to show that they're independent, or show that any one of these would be equal, would show that they're dependent. Wait, did I say that right? Any one of these to show that they're not independent, any one of these equal to show that they are independent. Okay, so the conditional probability of A given B is the probability of getting a spade. Let's see. A is the event, the second card. B is the first card, is the spade. So of getting a spade on the second draw, given that a spade was obtained on the first draw. In this case, a spade is removed from the deck on the first draw, so that 12 of the 51 cards, so if you remember about card decks, a quarter of the deck is spades, a quarter of 52, and a quarter of 52 is 13. So when you start out, you have 13 spades. However, you take one spade out, then you only have 12, and only 51 cards. So the probability of a spade on the second, given that you got a spade on the first, is 12 over 51, which equals 4 over 17. Now the question is that equal to the probability of A? Remember, A is... no, that's not right. Okay, yeah, that's what we're checking. Okay, yeah, they're going to do it that way. So the probability of a spade on the second is this one and this one. So we have to add up, go along here. So we multiply this times this, and go along this way, multiply this times this. That's what they do. This one times that one, plus this one times this is 1/4. So the probability of spade on the second is 1/4, and so that's not equal to what we got just up above here. It's not equal to 4 over 17. 1/4 and 4 over 17 are not the same, so they're not independent as we suspected. Okay, let's see something. Let's look at, let's read this part carefully. No, actually I want to read the part below that carefully, but let's try it now. In many practical problems, it is difficult or even impossible to determine with certainty whether two events are independent. In such situations, the experimenter often relies on intuition to decide whether to assume the events are independent or not. For example, suppose we know from past records that the probability is 0.9 that a certain sharpshooter will hit the bullseye on a target. 0.9 that they will hit the bullseye. Suppose we also want to find the probability that this sharpshooter will fire 2 bullseyes on 2 successive shots. We might begin by introducing the events A gets a bullseye on the first shot, B second shot. Thus A intersect B means that A and B occur, means that he gets bullseyes or she gets bullseyes on both shots. If we assume that A and B are independent, then we're assuming this. So that would mean 0.9 times 0.9, which is 0.81. Okay, so that's if we assume that they're independent. Okay, now let's read this one carefully. Be careful, many times in practice, events are considered to be independent and really are not independent. Since this computation is erroneous, if A and B are not independent, that is this one up here, this is erroneous if they're not independent, we should carefully examine this independence assumption. For A and B to be independent, the chances of getting a bullseye on the second shot should not be affected by the result of the first shot. That's what it would mean to be independent. It is possible, however, that a miss on the first shot might disturb the sharpshooter's concentration and reduce the chances of a bullseye on the second shot. Or it might increase the desire for a bullseye and thus improve the shooter's concentration, thereby bettering the chances. In this situation, the independence assumption would not be warranted. On the other hand, if the experimenter does not believe that this psychological factor is significant, he or she may choose to accept the independence assumption. Although there are statistical tests that can sometimes be applied to a test for independence experimentally, they are beyond the scope of this test. In any event, these tests cannot always be applied, so the applicability of the independence assumption often depends on the judgment of the experimenter. Okay? I'll let you read this example 10, and let's go down to here. A set of events. Now we've just been talking about two events, but a set of events is called independent if for each finite subset we have this equals that. So first of all, let's look at this. This is kind of familiar. Just like P of A intersect B should be P of A times P of B. Here we're saying that P of A1 intersect P of A2 intersect should be the product of those. So that's, if they're independent, this would be true. Now it says a little bit more than that. It says if you have a set of events, so this is part of that set, but not necessarily all of them. So what they're saying is if you take that set of events and you take any subset of that set, this has to be true for every possible subset. Okay, so it's a pretty strong restriction. Now, for example, here's a set. If we have three events, in order to say that these three events are independent, you have to consider all possible subsets of these three events. Now, actually, we only have to consider AB, AC, and BC. Those are really the only ones we need. But they have to be, you have to show that P of A intersect B is equal to P of A times P of B, P of A intersect C, and P of B intersect P of C. Okay? And this also has to be true. Okay, so it's a pretty strong condition. So here, in the manufacture of light bulbs, filaments, glass casings, and bases are manufactured separately. What does that say? Sorry. In the manufacturing of light bulbs, filaments, glass casings, and bases are manufactured separately and then assembled into a final product. Assume that past records show the following. 2% of all filaments are defective. 3% of all glass casings are defective. 1% of all bases are defective. So, sorry, let's look at this is just a good thing to remember. So if you have E intersect F equals some set of, we call these events, but usually we call them outcomes, then the probability of the intersection is equal to the probability of the sum of the probabilities of each of them. If E and F are mutually exclusive events, that means that their intersection is empty, and so the probability of their intersection is 0. If E and F are independent events, then this is equal to that. Remember, mutually exclusive is one thing, independent is another. If P of E union F, this and this are known, we can use this formula which we talked about. So this is just a review of the things that we've done. And in general, this will be true. That means you don't have to worry about independence here. This is just true always. And this. So that's a kind of review of what we've done.